So I don't know if you still remember yesterday, but we talked about, we started talking about regular expressions and regular languages. How visible is this back there? Good? Okay. And we spent quite some time talking about how to go from expressions to languages to prove one half of Kleene's theorem. Okay? So what I want to do today, I want to talk a little bit about the other half. How do you go from regular languages to regular expressions? And then I want to actually go on and give you the formal definition of what a Kleene algebra is. And then hopefully I will not have to delete this board, and I will show you what a Kleene algebra with tests is in the same place. Okay, so let's talk a little bit. This is sort of wrapping up yesterday's lecture, really. Let's talk a little bit about the reverse direction of what we saw yesterday for Kleene's theorem. Namely, if I have a regular language given by a deterministic automaton, how do I build a regular expression that denotes the same language? So yesterday we saw, if I start with E, how to map these to an automaton, A of E. And now we want to go the other way around. And like yesterday, there are many ways of doing this proof. There's the way the proof was done originally, and there's sort of more recent work on how to carry out this proof. So I'm not actually going to give you the proof in detail. I'm just going to show you roughly how this proof would go. So you start with a DFA, okay? And a DFA is has a set of states, let's say S. And for every letter in the alphabet, I have this. So I have this transition function that for every state and for every letter gives me the next state. Now, there is a way to see this transition function as a matrix. Namely, I can have a matrix. So the states are finite. So I can write down a matrix where I write down all my states. Let's imagine I have k states. So I write this square matrix, and I think of every row and column as being indexed by one of these states. And then when I have an entry here, I and j, I'm going to write here, let's say, I'm going to write a plus b for now and then explain what that is. I'm going to write a sum of all the letters that allow me to go from state j to state I. Okay, so in a deterministic automaton, I have all these states. So let's say that at some point I have a state Sj. And I can get to Si using multiple letters. And then maybe with letter C, I go to this place here. Okay? So I'm going to write, for every entry of that matrix, I tell you which letters allow me to go from Si to Sj. Now, as it turns out, this is just a representation, right? This is like, it's as if I was coming up with a data structure to store the information, the same information I have in this automaton. Nothing has changed. I'm giving you a way to represent the same information I have here as a matrix. And the only reason I'm translating this to a matrix is that now, once I have the matrix, I can start treating the matrix almost like a regular expression. So in fact, if I have a matrix, which the entries are in themselves regular expressions, because what I'm going to have inside is sums of letters, which are regular expressions, I can give you, for this type of matrices, square matrices, all the operations that we talked about yesterday. So the plus, I can just do pointwise plus, because it's a square matrix. The concatenation, I just do matrix multiplication as usual, but for elements, when I multiply, I use sequential composition. And so now the only thing I have left with is what would be the star of such matrix. And I will tell you that in a second. But if I have a star defined for this matrix, then I can actually talk about the regular expression of corresponding to a state in an automaton. Let's say I pick Sj, by just starting with the transition matrix, build the star of that matrix, and then multiply it with the vector that tells me which states are final and non-final, and then select entry j if I'm looking at state Sj. And this is kind of a very beautiful way of looking at this proof. It's actually, this proof is relatively recent compared to some other proofs. And again, I'm going to tell you a little bit about what you usually see in textbooks. But this proof is really algebraic, because it just takes the automaton and realizes that the automaton itself, if you sort of stare long enough at it, has the structure, the same structure as regular expressions. You just need to sort of get away from the fact that this is not just a function, but it has more structure, because these letters here, as I'm accepting languages, I'm really concatenating them in a way that corresponds to matrix multiplication. Okay? I will give some notes on the explicit definition of these things. I'm not going to do it now, but this is just a sketch. What is the usual proof like if you open some classic textbook like Hopcroft or Ullman? And this classical proof is in the lecture notes I posted yesterday. The classical proof approaches the problem a little bit more inductively and says, if I have an automaton with n states, I can slowly delete states and replace the transitions by regular expressions. And I will show you how to do that. And you delete states up to the point where you only have 2 states. And when you have 2 states, you stare and you come up with the expression. That's how it works. But up to 2 states, there's a method. And then for 2 states, there's a formula. So it's kind of how it works. So what does it mean to delete states? Right? So let's do an example. So this is called the state elimination. And this is described in a lot of detail in those lecture notes. State elimination method. And the idea is you can randomly pick. So if you have more than 2 states, you have to have at least 3 states. And you randomly pick one of these 3 states, let's say this one, to delete. So I want to delete this state. Okay? So let's write down some transitions. Let's imagine I only have A and B. And maybe this is what I do. Okay? Did I write all of them? A, B, A, B. Okay, so I pick this one to delete. Okay? So if I delete a state, how can I delete it without losing any information? Well, if I delete this state, I have to send this transition and this transition and this transition somewhere. So the rule is, if I delete a state, I need to make sure that any path that goes through that state is captured by the regular expression that denotes it. So if I have this structure here, what is the regular expression that denotes just this path here below? Yeah. So it's B star A, right? So B star A. And it so happens that I drew a small, sort of simple example, that the only thing I need to do is, so I'm going to delete all of that, and I'm going to replace it by a transition that goes from this state to this state, labeled by that expression. But I already have a transition between those two states, which is A. Okay? So instead of adding a new transition, I just add it here. Okay? So now I've deleted that state. Okay? And now I have an automaton that's not quite a DFA anymore because I have these regular expression labels, but we squint and we pretend it is. And now the question is, I only have two states, so what do I do with it? Let's make one of these states final. Okay, so let's imagine this state is final and this is the initial one. So what do I do with this object now that it has two states? So now that it has two states, I just need to calculate what this would be. Namely, I want to calculate every accepting path from the initial state to any final state. In this case, you know, it's itself. So I want to compute every path that goes from here to here. So what can I do here? Well, this one is, again, is relatively easy. I can just take a transition here, and I cannot stay there because it's not a final state. So I can take multiple A's, but then eventually I need to come back. Right? So the expression for this one, you can read it of the automaton is just this. Okay? But of course, this can get a little more complicated because I could have a loop here. Yeah, Nick.
Also, or empty.
Or empty. Good catch. Thank you. Was one, because this one is final. Okay, so you have to sort of come up with an expression for anything that, you know, that can potentially have a loop here. Then this one could be final and this one non-final. So you have to account for all two-state transitions. Okay? Yeah. Yes. And then you don't need the plus one. Yes, so what I had written was just one path back to here, but I can repeat that over and over. And probably I should go and check the solution because people keep raising their hands, so probably I wrote the wrong solution again. Yes?
If you end up, sorry.
Okay, take your time.
I guess collapse a DFA in multiple different ways. Will you get different regular expressions?
Yes. They will be equivalent, but they will be different. You know, the way you choose the state to eliminate could give rise to different expressions. Oh, thank you. The question was, if I eliminate states, different states, so if I choose to eliminate the states in different order, will I get different regular expressions? Yes, but they will be equivalent. Yes?
Can you eliminate that with some sort of indice ordering to the states?
So that in the proof and in the lecture notes, I just sort of like pretend the states are ordered, and then I do it ordered. But you can do it in any way that reduces the size of your set.
How do you prove that the elimination strategies are confident?
Well, it's a finite state automaton. And at every step, I eliminate one state. So eventually, I have to get to two states.
Sure,
I prove that every elimination step does not change my language. Right? And you see that, I mean, this is not a proof, but the way I did it, right, I did not lose any information. So you have to show that the way I write that expression is exactly the language of the state I eliminated. Okay? And because I do not touch the transitions of the states that remain, I end up with the language, you know, the concatenation of those three languages, the language of the first state, the one I eliminated, and the other one. But yeah, it requires a proof. Yeah.
There is another matrix proof.
Yeah.
Which direction was it proving? Is it constructing the machine?
So the matrix proof, you start with an automaton, you take the transition function and turn it into a matrix, then you compute the star of that matrix, and that gives you the regular expression for each state. So it goes from automata to expressions. Okay, more questions. So this, I mean, one there, sorry.
Quick question. So it seems like you have to at least have one accepting state at the end for this to work.
Okay, so the question is, it seems like I need an accepting state for this to work. Okay. As I said before, when you are squinting and trying to come up with what expression corresponds to a state, to an automaton, you need to look at all possibilities, right? So how many possibilities do I have? I can have that. I can have that, and I can have that. Right? So there are 4 possibilities in terms of final, non-final, and then the transitions can be arbitrary. Okay? So what happens in this transition, in this automaton here? Who has ideas? 0. I mean, I could read the path and write a very complex expression, but then I would have to multiply it by 0 because this state is non-accepting. So you don't necessarily need to have a final state, but if you don't have one, then the expression is 0.
So what if I say I had originally my it has a accepting state, but then during my deletion process, I delete that one particular accepting state.
Right. So when you delete the accepting state, you're going to be transferring stuff to the expression. That's one thing. But in the process, if you do have a final state, if you have just one, you do not delete that one, because otherwise you need to do some extra stuff in this translation. So you are right that there is, in the deletion process, you have to be a little careful with the final state. So there's a sort of case analysis in the end. But if you have multiple final states, you can just delete. Other questions? Yes?
I assume the same holds for non-accepting state, because you need at least one state to transition to where it won't just accept anything.
Pretty much the same answer, right? You need to basically account for all your possibilities, yeah. So the question was whether this also applies to non-final states. So in fact, in the proof I have in the lecture notes, I think I don't remember, but I think I wrote at the top, without loss of generality, I assume that I have an automaton with at least a final state. And then these cases I actually treat as single state automata, the ones that have both final or both non-final, because I can delete them. Okay, so these, in fact, in the lecture notes, these are the 4 cases I look at. Either it has at least a final and non-final, or it corresponds to a singleton. Okay. Yes?
Is there any particular reason we would want to use one of these proofs versus the other? Do they have any? Do they have different use cases?
So the one with the matrix is very convenient for what I'm going to talk about next. So the one with the matrix is algebraic, and this actually generalizes better than the state elimination one. So when I talk about Kleene algebra with tests, and hopefully tomorrow about netcat, the state elimination one doesn't generalize, which is a little sad. Okay. Whereas the one with the matrix sort of is a little more robust. Okay, so we sort of been talking about regular languages and regular expressions. And we already briefly touched upon this, but if I give you two expressions, you know, if I ask all of you to write an expression that describes a certain language, like the language of words that has the number of ones is divisible by 3. You know, if I ask you to write a regular expression that denotes this, we might end up with very different regular expressions across the room. This is actually an example of a language where the automaton is much easier to write than the expression itself. There's not many examples like that, but that's one of them. So things that involve counting are usually better with automata. And so when you have these expressions, you want to reason about whether they are the same. And one way to reason about whether they are the same is to build the automata and then check that the automata, when, you know, accept the same language. And at that point, to check that the automata accept the same language, there's also many methods, which I will talk about in a moment. But we can think of the expressions as just pure syntax, and we might want to reason about the syntax. So the question that Kleene left open in his paper was, is it possible to write a finite number of equations that allow me to always answer this question? Given two regular expressions, is one equal to the other? Okay? And there have been different answers in the literature, so I will show you one, which is the definition of a Kleene algebra. So a Kleene algebra is a set that obeys the following rules. So it's a set, let's call it K. I'm going to write it up here so that I have more space for the equations. The set K, together with constants 0 and 1, and operations plus, sequential composition, and star, so it's a tuple of things. And this tuple satisfies the following things. Plus is idempotent, commutative, associative, and has a 0 element. Okay? For those who have done algebra before, you might recognize this as the laws of joint semilattices. So the plus together with the 0 forms a joint semilattice. The times is commutative, sorry, is not commutative, it is associative. It has a 1 as a neutral element, both on the left and on the right. And the 0 is an absorbent element. Okay? And these first two equations is what is typically called a monoid. Okay? So these things here, this is a monoid. Okay, the times distributes over the plus. Both on the right and on the left. And so if I take all of this together, I have another known algebraic structure. Who recognizes this? A semi-ring. Okay? So I have a semi-ring. So what is missing? So I've sort of given you the structure of plus and times and 0 and 1. Yes?
Sorry, is the equivalence relation part of the structure, or is it
So I say that a Kleene algebra is a structure in which the operations obey these equations.
But is this in the sense of mathematical equality, or is this in the sense of some other kind of equivalence that we're now defining?
This is in the sense of a syntactic equivalence. Okay, so it's not part of the tuple. I'm going to be quotienting. I'm going to be talking about things like, you know, let's say, if I look at the regular, I'm going to give you examples of structures that satisfy these. So let's say regular languages. If I take or all languages actually, take all languages with union, concatenation, empty, the empty set, the set with the empty word, and Kleene iteration. So that tuple, together with language equality, satisfies this. Okay, does that make sense? So you sort of like you have to tell me what this is for each model. So if I pick K to be 2 to the A star, then I need to define this relation over K, over the specific K you're looking at.
So it's a property of K rather
Yeah.
than a feature of the algebra structure.
Exactly.
Okay.
Yeah. Okay, so the thing I'm missing, I haven't told you what star obeys. Okay? So I want star to sort of, whatever I write down for star, it has to capture the fact that I'm iterating the expression. Okay, so I want star to be some form of fixed point. And so the first thing that I will write down is that star is indeed a fixed point. And you can unfold star either on the left or on the right. It doesn't really matter. So this just says if you have an expression starred, it has to be equivalent to doing nothing or running E once followed by E star. Okay, so this is typical loop unfolding. But it's not only a fixed point, it will be, I'm going to write it as a list fixed point. So I'm going to talk about an order on expressions. I'm going to talk about E being smaller than F when E plus F is E. This is what sometimes is referred to as the natural order on a semi-ring. Okay, so I define E being smaller than F if E plus F is E. Think of sets. I have a set is a subset of another set. If when I take the union of those two sets, the smaller one is F, yes. See? Now that I was saying it out loud, the smaller one disappears, right? So if the smaller one is contained in the larger one, when I take the union, all those elements are already in F. Okay, so it's the same thing here, but syntactically. Okay, so as intuition, think of this as subset. Okay, so now I have an order. This is a partial order. It's a complete partial order. And I'm going to now write down how I can actually compute a star. Okay? Now I need to, I never know this by heart, so I need to look at my notes. Okay, so here's the rule. It says if I can prove for some x that Ex plus F is smaller or equal than x, then I can derive from that that E star F is smaller or equal than x. So let's go through this. What does it mean if I can prove this, right? It means that I can iteratively replace x by Ex plus F. And I can build this chain of things that look like F, E, F, E, E, F, E, 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 F, and so on, which is exactly what E star is doing. So E star F is just doing, F, E, F, E, E, F, and so on. So this rule allows me to go from a recursive inequation, because you see you have the x appearing on both sides, and it tells me that the solution of these, the least solution, is E star F. And this is the left rule, and you can do a right rule as well, where the x and the E are swapped, and then the F and the E star are swapped. But the left rule is enough. Okay, so this basically tells me E star is the least solution of this iterative inequation. Okay, so this thing here axiomatizes E star as a least fixed point. So what is a Kleene algebra? A Kleene algebra is a semi-ring together with a least fixed point operation. Yes?
Can you explain the logic of why the F is allowed to stay? Because the top, at the top it's plus F, right? If I read that correctly.
Yep.
Okay.
At the top is plus F, but I have the x here, right? So at some point, so this plus here gives me two alternatives. Either I continue or I stop. Think of this as an if then else.
Okay, so why does the bottom also have to?
Why does so if I stop, if I decide to take the F branch, I can't do anything after that.
Oh, wait. Okay.
So once I reach F, I'm done. Okay, so F is the stop condition. So if I write a 1 here, if I replace F by 1, okay, I could delete the F here. Okay? Okay, so yes. Once I hit F, there's no recursion.
I guess that's true on the left, but since we haven't specified what x is, I guess
X is a variable.
yeah.
So this is what makes this very counterintuitive, right? You are going to use this rule in specific instances of X, where X is a specific expression. But as I wrote it here, you can think of this as an axiom scheme. So in fact, this negatively answers the question that Saloma left open. Saloma conjectured that there was a finite number of equations. And that's not true, because this last one is not, first of all, is not an equation. It's a Horn clause. And second of all, it has this variable that really turns this into an axiom scheme. Okay, that's the way, one way you can think of it. So I'll put up some exercises where you can maybe apply this rule a couple of times and see how it works. Yes?
Trying to understand, why does the premise give us the, like in the conclusion, the case where you do E 0 times, why does that issue from the premise? Because I'm thinking if you set f to be 1, then you would expect like x equals 1 to be a valid solution. Oh, wait, never mind. Sorry.
Okay. You answered your own question. That's good. Okay. Other questions? Yes.
So the phrase least fixed point to me suggests a map for which this operation, this E star, is a fixed point of some map from the Kleene Algebra to itself.
Yep.
Could you clarify what that map is right here?
So you're looking for a map like this, like a map from
Yeah, from phi. The idea is
phi from
what
expressions
phi should do is send E to E star. Well, E star will be like the smallest element, which is a fixed point of this map, phi.
So, okay, so there are two things here, right? This is the least fixed point of this order, okay, which is an order on expressions. And the map is going to send expressions of this form, right? So you have this inequation here is going to be transformed into this equation here. And this is in the same, I don't know if Paul showed this in this lecture because I went out to buy chalk, but you know, when you're doing induction on the rules of lambda calculus, you do the exact same thing. You have a rule, a derivation rule like this, and you look at the fixed point defined by a rule like this. So you have, think of these as like you have a set here of expressions I, and the transformation you have here below will be your phi of I. Okay, for every expression in this set I that satisfies this inequation, you can apply this rule here. So this rule is axiomatizing the thing as a least fixed point, sort of giving you the syntactic way of computing your fixed point. It enables you to replace something that has no star and has a variable by something with star. Okay. I can show you an example of this, if this is helpful. Or I can leave it as an exercise, and then if you cannot solve it, I can show the solution tomorrow. I think I actually had some exercises on my notes. Let me see what exercises I have. Exercises. There we go. This is homework. Here's a fun one. This last one is hard. It's probably the hardest of these exercises. This is the rule we saw yesterday, the denesting rule. Okay, so these are four exercises that will give you some practice with those rules. And a lot of it is syntactic, so it takes a little bit of practice to getting used to. Yes?
But you're applying anti-symmetry of the relation yet for these?
You can, yeah. Most of the times is the way to go. Sometimes, oh, are you applying, sorry. The question was, are you applying anti-symmetry to get those? And basically, I mean, in many cases, you can directly get the equivalence. But when you have a star, it is often a good assumption that you need to do it in 2 steps. Okay? Okay. So this side of the board, everything is syntactic. Like I haven't told you anything about K other than it's a set with some operations and it satisfies these equations. Why is this actually useful, right? This is useful because there are many examples of structures like this. One example is 2 to the A star. So the set of all languages. So the set of all languages together with together with union, concatenation. I should write this in the right order, but I wrote there, which is together with the empty set, the set with the empty word, union, concatenation, and star. This is one example of a Kleene algebra. If I replace 2 to the A star by regular languages, so the subset of 2 to the A star that's regular, this all still works because all these operations are closed under regularity. Now, these are sort of the boring examples. What are more interesting examples of something that satisfies these axioms? One very cool example that has some applications in verification is relations, binary relations. So if I take binary relations over some set of states, so let's call it rel or B-rel for binary relations, then I can take the empty relation, okay? I can take I'm going to call it delta, the diagonal relation that relates just x to x. I can take union of relations, and I can take relational composition. And then for star, I can take, does anyone know what star is for relations?
Transitive closure.
Transitive closure. So, okay. And you can check that all these operations here satisfy these rules for just set equal. Right? If I start with a K and I look at square matrices over K, ooh, this color is pretty unreadable, I think. Let's use one of Frank's chalks here. If I look at square matrices over K, and I extend the operations pointwise, okay, so no, let's do this again. So the matrix with, you have the zero matrix, you have the diagonal matrix with ones on it, And then you take pointwise plus, you take the multiplication of the matrix by using the element k. So k has this multiplication, so I use that for the elements. And then what do I do with star? Okay? And I don't know the formula by heart, so I'm going to look at it. So what do I do with star? This was the thing that I said I would tell you at some point. What I do with star is that I define it for a matrix that's 2 by 2, and then I inductively extend it to any square matrix. So the 2 by 2 matrix is interesting because it goes back to that two-state automaton we were staring at some point during state elimination. So the way to think about this is that this is a two-state automaton that has a loop with A in the first state, a loop with B in the second state, and it transitions from the first to the second with B, and from the second to the first with C. Okay? And I'm going to write down this formula, and then I'm going to write down the first one. Okay, this is not going to fit here, clearly. Okay. So the star of this 2 by 2 matrix is going to have in the first element this expression. Let's see if we convince ourselves that that makes some sense. What is this expression telling me? If you remember that example that we looked at. So this is A, B, C, D. Okay? What is A plus B, D star C?
How to come back to it?
So this oh, I heard someone say the answer.
All the ways you can get from the first state back to itself only once, right? Well, right, without the star.
Yeah. So if I look at the whole thing with the star, then what I have is an expression describing all paths from 1 back to 1. Okay? And that's exactly what the entries of this matrix are going to be for every single entry. So if I look at the entry 1, 2, I'm going to write every path from 1 to 2. Okay? So in this case, and I'm going to do a little bit of looking at my notes so that I don't make a mistake. Right. So I get, so from 1 to 2, I get A plus B, D star C star, followed by E, D star. So if you look at it, it has the first expression there, right? So this is what this is saying is, if I'm going from 1 to 2, I can go many times from 1 to 1, because it doesn't matter. And then at some point, I need to take a B to get to 2, and I need to stay in 2. Okay? From 2 to 2 is a sort of symmetric thing to the first, to 1 to 1, where you sort of, the A becomes D and the D becomes A. Okay? And then here on this side, you get something very similar. This is in the notes as well. Okay, so I've now given you a 2 by 2 solution. And I think I can convince you that this looks right. But I mean, it's just a definition. I'm just giving you this as a definition. And then I can extend this 2 by 2 matrix to any matrix. Because basically, if I have, say, a 3 by 3 matrix, I just split it into 2 by 2. And I first compute the solution of the smaller one, and then I replace it in the rest. Does everyone see what I mean? So if I have a 3 by 3 matrix, I can split it, say, like that. Okay? And then I can extend by computing solutions piece by piece. Okay? So I can inductively basically use this formula to go to larger and larger matrices. Okay? And then, of course, I will have to check that that star satisfies this thing here. And the proof is actually not so hard because these are square matrices over a K. So we know that the elements satisfy this solution. And then I basically just, again, inductively show that the definition I gave here for square matrices to satisfy. It's a little bit tedious proof, but it works. Okay, and these square matrices over Kleene algebras play a big role in then proving that you can show that two expressions are, if two expressions denote the same language, then they are indeed provable using just the axioms from Kleene algebra. Okay, and that's, let me write that down. That's one of the main results. This is a result due to Posen in 93 that says if two expressions have, actually if two expressions E and F have the same language, then I can prove that E is the same as F using the axioms of Kleene algebra. Okay? So this direction, so the direction from, you know, that I go from syntactic to semantic, syntax to semantics, this is what is called the soundness. And this here, it is called completeness. So soundness just really tells me that regular languages are a model of Kleene algebra, which we already convinced ourselves a few minutes ago. Completeness tells me that not only they are a model, regular languages are a model, but they are the model. In fact, they are the free model for that algebraic structure, meaning that it's sort of the minimum structure that I can have to describe a Kleene algebra. Okay. And this could be a whole course in which I then would teach you how to actually prove completeness. I mean, this takes a few lectures, but I want to give you a glimpse of what that proof looks like. And then if I get invited to teach again, maybe I spend a whole course on this proof. Or maybe this is my way of not getting invited ever again. Okay. So I want to prove that if I have two expressions that have the same language, that they can be provably equivalent. Okay? Let me just make sure I give you all the steps. So how would I do, like how does this proof go in Cozen's paper? And again, there are different proofs of this, but this is the structure from Cozen's paper. So in Cozen's paper, what he does is the following. For every expression, he builds a non-deterministic finite automaton. Let's call that A of E. And what he uses to build that automaton is very much what I mentioned yesterday, it's a Thompson construction. We have a more recent proof in which we build directly the deterministic one. But in the original proof, he builds first a non-deterministic automaton, and then he determinizes the automaton and gets something else that I'm going to call A prime. I should make these arrows a bit small. Okay. And then from here, he minimizes these automata. Okay. And when you minimize these automata, and let me write maybe this as 2 steps. Let's call them M for minimal. Let's see. So he gets these 2 automata, M of E and M of F. And if 2 languages denote, if 2 expressions denote the same language, it is, I don't know if I mentioned this yesterday, but every DFA has this nice property that it has a unique minimal automaton. And this is unique modular renaming the state names. But like it has, once you fix the number of states, it has a, once you fix the language, there's a unique minimal, state minimal automaton. Okay? So if I know that E and F are 2 expressions that denote the same language, and I know that these are the minimal automata accepting those languages, then these things here are isomorphic. They might be different because I named the states differently, but they are the same automaton. Okay? So what Dexter does in this proof is basically going first all the way down to the minimal automaton, and then going all the way back up to a proof. So how does he do that? Well, this is where matrices come into play. So every single object in this little diagram is a matrix. And not only it's a matrix, remember how yesterday when we were building the automaton, the states themselves had expressions? The name of the states were expressions. This is actually a matrix of expressions. And so as he's going down this tree of transformations, what he shows, and that's where the sort of hard work is hidden, is that every single of these constructions can be proven sound just using the axioms of Kleene algebra. So going from E all the way down to ME, I did not change the language, and I only use axioms from Kleene algebra. And I do the same thing from F all the way down to MF. And when I make it here, I have found a canonical form for my expressions. And so sort of this, there's a finite sequence of steps that transform Z into the canonical expression and F into the canonical expression. And therefore, E is equivalent to F. Okay? This is the core of the proof, but these are like 2 lectures to show you all the details. Because every single detail, like someone pointed out before, you have to actually prove that each of these constructions is sound. And I can hand wave, and I can show you some examples, and you will sort of be convinced. But ultimately, you have to prove soundness of every single one of these arrows. And you have to show that you can do them syntactically, just using the axiom. Okay? This first step
Yep.
is non-deterministic.
But
So in the original proof, he breaks these into two steps. He first gets a non-deterministic automaton, and then he determinizes the automaton.
but it is finite during the whole process.
It is finite during the whole process. Everything is finite because I want my matrices to be finite. Yeah. Okay, so this is maybe my next OPLSS course, how to prove completeness. Okay, let me see how much time do I have. 15 minutes? Who is 15? Okay, great. Great, because that means I am on time. Now, why did we spend almost 2 lectures talking about basic stuff like automata and regular expressions? Because we are now set up to add something to it that will allow us to reason about simple imperative programs. So I have this structure, right? And I have this set K, which can be many things. And I have this 0, 1 plus time, sequential composition and star. So it almost looks like I can talk about imperative programs. What am I missing to talk about imperative programs? States. Not only. What else am I missing? Well, okay, let's go with state. What type of state?
Like a store or for variables.
For variables. Let's say I only have Boolean variables. Okay? I'm still missing a state. I'm missing the value.
You're missing conditionals.
Yeah. I want my, which is connected to state if I assume I only have Boolean variables. I want to be able to make statements like if P, then P, else Q. Okay? And this B is basically testing my state. Is a test on my state. So what I'm missing here, I'm missing a way to talk about these tests that appear in these control structures. I mean, I could write things like B0 or B1, right? I mean, if I have a bunch of tests, I can talk about combinations of these tests. B0 and not B1. There's all kinds of things I might want to write there. But right now, this structure doesn't really allow me to do that. So what I need to somehow, inside K, so I want K to be a set that talks about programs or program actions, but also that talks about tests. And not only talks about tests, but actually captures the fact that those are tests, meaning that I can do or, and, negation, all kinds of things that you can do with tests. Who knows what is the algebraic structure of tests? Boolean algebra. So what I need to somehow combine Kleene algebra with Boolean algebra. Okay? This is what I need. So how do I do that? I'm going to say that I'm going to add one more condition on K. I'm going to say that K has this special friend called B, okay? And this special friend B is so special that if I use the same operations as the Kleene algebra, except star, and I somehow magically, inside B, I have this other operation, which I'm calling bar. This subset of K is a Boolean algebra. Okay, so what is this exactly in the sort of simple, when I'm building one of these things? It's like I have a set of letters. So you remember, like in the automata, we have the alphabet A, from which we build regular languages. And in that set of letters, I'm going to color some of those letters red. And those red letters, I'm going to use as program actions in the same way. But I'm going to give those red letters a companion. Namely, I'm going to give every red letter, and now I don't have red, so this is kind of a bad analogy. If I have red in here. Okay, so I have my set A of program actions. So I have this big set A that I'm using to build my regular languages. And, you know, inside this set A, I have P, Q, and then I'm going to have a bunch of letters, finite number of letters, that I'm going to color red. And for each of them, I'm going to make sure they have a barred friend. And this is just syntax. I'm just sort of reserving a bunch of letters and calling one. Okay. Now, this red part of my alphabet, I'm going to use to talk about tests. And the yellow part, I'm going to use to talk about program actions. But as I look at generating K, I can use all the letters. Because the red letters, they are a bit like assert. If I use them in the middle of a program, they are just asserting that a certain test is true. But if I use them in a conditional, I'm going to think of all those red letters as forming a Boolean algebra. And that's why I gave them sort of barred friends, because then I can define this bar just inductively. Okay. Now, because I'm asking B to be a Boolean algebra, the equations I have here are not enough. I'm missing some equations of Boolean algebra. Okay. So what am I missing? Oh, before I say what I'm missing, let me just make one remark. So this B is inside the Kleene algebra, meaning that this plus, this is the plus of the Kleene algebra, but when it comes to B, you really should think of it intuitively as or and and. Okay, so for elements of B, whenever I'm summing elements of B, I think of it as I'm doing an or. Yeah?
Do those operations have to be the same as in the first two?
Yes. Yes. So when I wrote B is a subset of K, I should really have written that it's a sub-algebra, meaning it's the same operations, because K, you know, K is this big set, and inside this set, I'm finding B. Okay, so I want these operations to really be the same, because otherwise I have a problem. Okay? But because these operations are the same, now I need to add certain things. So namely, if I have an element from B, and I do B plus 1, what should that be? Right? So the 1, in terms of B, is true. So if I do B or true, in in Boolean algebra, I get what? True. So I'm writing these equations in blue because they are different. Note that the plus 0 here holds, so B or false is B. That still holds from the general equations. But this one only works for things in B. Okay? And there's one more I'm missing, and I forgot which one. Let me see which one am I missing. Right, I'm missing the De Morgan laws. Because nothing here talks about not, right? So not is a new operation, only for elements of B. And what does not satisfy? Let me find some space. Not will satisfy the things you expect, which if I have A plus B from elements of B, this is the same as not A, not B.
Can you use a different color?
Yes. Is that better? Okay. If I have was not B, if I have 0 not, that is 1. And, and I also have, and this is important, that if I take elements of B and if I concatenate them, then for elements of B, concatenation is commutative because it's just AND. This is not true in general. In general, if I have two expressions, they don't commute. But if those are elements of my test, if these are tests, it's just conjunction. So conjunction is commutative. Did I forget something?
Yeah, not one.
Sorry?
Not one.
The not one. No. Oh, yeah, I know what I forgot. I forgot that not A is A. And you can then get this other one. Okay? So you just need not A is A. Yes? Indeed. That's a good question. What happened with the star? So for the Boolean part, I don't have star. Star is something that I only have to define for the whole K. And when I define it for the whole K, in effect, I'm only also defining it for elements of B. But B, to be a Boolean algebra, only needs to have defined the operations of a Boolean algebra. So or, and negation. B, so B is closed than the star in the sense that you can show that any B star is 1. So that's an exercise. Any B star is 1. Okay? Yes?
When you say that concatenation is commutative for B because it's just AND, my understanding is that B is supposed to represent tests in a simple imperative language.
Yeah.
Are we assuming that this imperative language has no effects?
Very good question. Okay, so the question was, am I assuming that my language has no effects? Because I'm saying that I'm asserting that this fact is true. Yes. If it has effects, this whole thing breaks down. And in fact, again, I could give another course on this. If you try to do concurrent Kleene algebra, where you have parallel threads that can change the state, concurrently, then this will not be true anymore. You have to be extremely careful about asserting this. And there's a there's a nice example on why this breaks. But so in this setting, I'm assuming sequential, no effects. Like really, what we're trying to do here is a control flow graph. That's it. Okay? Things with effects get much more interesting. Okay, yes?
So about effects, I mean, if for conditionals we have to add the Boolean algebra, for like other features of programming languages, I suppose we also need algebra. So how further can we push this? Like,
So the moment I add concurrency, meaning I have some form of parallel threads, you cannot use directly a Boolean algebra. You have to use a slightly more enriched structure of tests, and you can use something that's called a partially commutative distributive lattice. And then in that setting, you can actually reason about threads. And the reason why you need the lattice is that you sort of want to sort of keep track of your interleavings and how they change the state. If you do it with a Boolean algebra, there's actually a paper on this that there's a paper that basically takes what is called a concurrent Kleene algebra, which is a Kleene algebra with parallel, and mashes it with Kleene algebra with tests as an algebraic structure. So it's a paper about algebraic structures. And they say, okay, look, just put it together, everything works. Except once you put this together with a parallel, with some reasonable laws, you can prove that every program, true is an invariant of every program, which basically sort of makes the algebraic reasoning completely useless from a program verification perspective. So it's sort of like algebraically, you could put them together, but then what you can prove with them is not very interesting. So in order to actually get something of combining tests and parallel, and also other effects like coin flips, if you have a language that allows you to do sampling, then you need to be extremely careful about how you treat your tests. And in particular, this axiom that you can permute tests is not true anymore because the effect might come in between, right? So when I'm, it's like the chicken crossing the road type of situation. The chicken looks right, nothing is coming. The chicken looks left, nothing is coming. And then she crosses the road and gets hit by a car. Because in between, the car came, okay? And so this is how atomic statements work, right? You want your true value to still be true when you're doing the second action. This is how I convinced myself that that algebraic paper was not quite right. It's because you want to be able to let the chicken not die. Anyway, okay. Oh, no question. That's okay. Someone was just scratching their head. Okay, I think I'm gonna kind of stop here. This is a good place to stop, and I think time is right. Yeah. Time is right. So I'm happy to take more questions at this point. And tomorrow, I can tell you what we're going to do tomorrow. You remember how we sort of instantiated K in sort of this for different models to do different things. I mean, I didn't show you what you can do with the models, but you can imagine. Tomorrow, I want to show you that you can instantiate B also in some cool ways. And in particular, if you instantiate B and K at the same time in some very specific way, you can reason about reachability in a network. So that's kind of a big leap from this. And one parting thought that I forgot to say before. If I have if then else, what is the regular expression that models if then else, now that I have tests? BP plus not B Q. And how do I model while loops? BP star not V. So if I give you a program written in this simplistic language, you can just translate it to a regular expression. And then using the axioms, you can actually do program transformation. And you can do some very cool things like compiler optimization, prove certain compiler optimizations sound by just using the axioms. Okay? Okay, so let's stop here, and tomorrow we're going to move on to a special cat called netcat. Thank you.